Hi everyone, welcome back. I'm Professor Rhett Smith from ProtonGuru.com, and today we're going to start with Lesson 4.2 and continue our study of pi conjugated molecules. In our last lesson, we learned about the difference in stability for conjugated versus isolated alkenes. So if a carbon-carbon double bond is pi conjugated, its reactivity is going to be different from that of a CC bond in an isolated alkene as well. Let's think about one of the first reactions we learned in Section 3 of our book for 1-butene reacting with a hydrohalic acid. Say we're doing HCl. So HCl plus 1-butene. Well, what happens? Well, you first do the electrophilic addition of the proton. Remember the mechanism from this. Make the more stable carbocation with some selectivity to have the cation on the secondary site instead of the primary site. You have the Cl- floating around that does coordination. So the overall result is that you simply add the chlorine to the more substituted side, the H to the less substituted side. Here we happen to have made a chiral compound, so we'd have a racemic mixture for this. If we consider the reactivity of the pi conjugated 1,3-butadiene, for example, well, we'd still have our strong acid undergoing dissociation in solution. That's what strong acids do. And you'd still expect the pi electrons to be attracted to the H+ to make the most stable carbocation. Now in this case, the carbocation that you make from that electrophilic addition step is this carbocation here. Remember though that this carbocation being beside a double bond actually has the potential for an additional resonance contributor to the structure. Remove the plus charge here. So what effect does this have when we think about the reactivity of the molecule when you have two potential resonance contributors for that intermediate that wasn't the case when we tried the reaction with an isolated alkene up here? Well, I've shown here again just what I drew in the previous slide, but I've numbered the carbons. You always number the carbons in the pi conjugated system from 1 to 4. You only number the carbons that are in the double bonds. Right? There might be substituents coming off or whatever, but you number those systems because we're talking about the reactivity of just that sort of pi conjugated unit in the molecule. If we do that numbering and consider each of the two resonance contributors that I've drawn, we can produce a resonance hybrid structure. In the resonance hybrid, you'll see that once the H+ has added the carbon number 1, right? There's the H already added to carbon number 1. We have partial positive charge on both carbons 2 and 4. Well, if you've got two sites of partial positive charge, compared to over here, one site that was positive to attract the anion, you actually have the potential for the anion to be attracted to carbon 2 or to carbon 4. And this could lead to two potential products. Right, we have one potential product where the H has added to carbon 1 and the X- has added to carbon 2, leaving this other double bond alone. But in the other resonance contributor, you have some partial double bond character here, and the X- is attracted to the carbon number 4. 1, 2, 3, 4. So in one case, you've added the H and the X to carbons 1 and 2. In the other case, you've added the H and the X to carbons 1 and 4. So which of these products is correct? Remember, when we talk about isolated alkenes, we talk about Markovnikov's rule, and that helps us figure out which product is the major product. And that's usually what you're interested in as a chemist, to figure out which product will I get the most of. Well, you can actually change your conditions and choose which of these products you want in certain circumstances. The 1,2 addition product generally forms faster. Remember that reactions that are faster have a lower energy of activation. And I'm going to call this the EA, energy of activation 1,2, because it leads to the 1,2 addition. And I've shown that in this diagram down here. The 1,2 addition product would have the small energy of activation. That means it's the faster reaction when we consider the kinetics. Kinetics is the study of reaction speed. But hold on a second. If I look at these potential products, I have a monosubstituted alkene that's the 1,2 addition product. I have a disubstituted alkene that's the 1,4 addition product. Well, we know that the more substituted alkene is more stable. We learned that way back in lesson 1.11, and we applied those ideas in thinking about the Zaitsev's rule in elimination reactions to make the more stable alkene. So if I draw the relative energies of the potential products, the 1,2 addition product that we said formed faster, and the 1,4 addition product that's more stable, how do we figure out which reaction is going to take place to lead to our major product? And why is the 1,2 addition product faster? We said it is faster, but we didn't say why. Well, if you think about the process where we take the HX and you have H floating around and the Cl- is kind of attracted to it. You do this addition. Once that H has added to this carbon here and made the plus charge, the Cl might be floating around in the proximity of that plus charge, and it won't have to float around and find the other site at the 4 position. It's a little further away. So the fact that 1,2 addition product forms more quickly is known as a proximity effect. It's because of this proximity effect that the 1,2 product, as we call the one where we add something to carbon 1 and 2, is formed faster. It is known as the kinetic product because the term kinetic only refers to how quickly a product is formed, not which of them is more stable. So the 1,2 addition product is always the kinetic product. But the more thermodynamically stable alkene that you can make is always what is called the thermodynamic product. Now, one confusing feature of this is that the thermodynamic product might be the 1,4 addition product, but it might be the 1,2 addition product. So let me explain. First, let's take a look at this pi conjugated system, which I've numbered 1, 2, 3, 4, numbering again only the carbons that have double bonds going to them, not starting way out here as if I was trying to name the compound. In a case like this, where each of the double bonds has different substituents, you have to start out by figuring out which of these will react to lead to the most stable carbocation. Remember, just like in the isolated alkene reactions we talked about, the more favored pathway will go through the most stable carbocation. Well, we want to place the positive charge in a position where it will have resonance. So let's consider doing this reaction where we take the H plus and react it like this to the electrophilic addition. We could place the carbocation right here and the H here. H could add to carbon 1 if we number it from that direction. This carbocation is stabilized by resonance. If, on the other hand, we number the carbon chain, the pi conjugated segment, the other way, and we have the H plus add to this carbon, we will get an alternate carbocation that looks like this. Again, following a rule that the H plus will always be added to carbon number 1. And here we've had 2 potential ways to number the chain. We now have to decide which of these 2 is the more stable carbocation. Well, let's look at this carbocation first. This is a secondary carbocation. If I move the pi bond from here to here, then the positive charge moves here. So I have 2 potential secondary sites where I can put the positive charge. And the double bond could be here or here. So it's secondary with resonance to secondary. Let's take a look at this other carbocation. If I consider the additional resonance contributor where I move the double bond here, like that, the plus charge will move over here. So it was a secondary carbocation with resonance to a tertiary site. So the double bond could be at either of those 2 sites, partial plus, partial plus. Now if we consider secondary with resonance to secondary versus secondary with resonance to tertiary, a more substituted carbocation is more stable, so that's going to be the preferred reaction pathway. Now we've already added the H to carbon number 1. If I draw out both of the resonance contributors individually for the carbocation that we figured out would be the better one here, then I can have coordination of the Cl- either to carbon number 2 or to carbon number 4. So the chlorine will make its bond to whichever carbon had the plus charge in each structure. So the question is, which of these is the kinetic product? Which one forms more quickly? Well, let's look back at our rules. The 1,2 product is always the kinetic product. So this will be our kinetic product. It's the 1,2 product. Which of these is our thermodynamic product? Well, we say here that the more thermodynamically stable alkene is going to be the thermodynamic product. So let's take a look at the alkenes. This alkene is di-substituted. It's got 2 carbon substituents coming out of the double bond carbon. But this alkene has 1, 2, 3 coming out. That's a tri-substituted, more stable alkene. Since it is the more stable alkene, it is also the thermodynamic product. So the 1,4 addition product here is neither the kinetic product nor the thermodynamic product. This is an extremely important thing to be able to figure out, because now we're going to learn how to control the reaction to get either the thermodynamic or the kinetic product by changing the temperature. So how does the temperature influence the ability to choose your product in these reactions? Well, if you have a choice between a few different reactions and you have a low temperature like this, low temperature means you don't have very much energy. It's much easier to get over this small hill than the large hill. So you're going to favor the reaction that has the lower hill. The lower temperature then favors the kinetic product, the one that has the lower energy of activation, the lower hill to climb. You don't have very much energy at a low temperature, so you're always going to get the kinetic product. Well, what if we do this reaction at a very high temperature? Well, at a high temperature, you have the energy to climb even the high hills. And once you're over here at the product, you can climb this hill and go back. You can reach an equilibrium. Remember that when you reach an equilibrium, the most stable product is the one that ends up being favored. So if the 1,2 addition product happens to be lower in energy, like the previous example, then you'll make that as your thermodynamic product. But you also have enough energy to climb the hill, no matter how high it is, if the 1,4 addition product happens to be the more stable. So whichever one is the more stable will be the major product. This is called the thermodynamic product. This will happen if you do your reaction at a higher temperature, say heating it above room temperature. So at high temperature, you will always get what is known as the thermodynamic product, which is always the most substitute alkene. Sometimes it's 1,2 addition product, and sometimes it's the 1,4 addition product. You have to work out the two potential products and choose the more substituted, more stable alkene in these cases. And that represents the addition reactions to conjugated dienes. And these rules apply whether you're adding HCl, HBr, Br2. Always add the first thing to carbon number 1, and then evaluate on the basis of your temperature and the relative stabilities of the ending alkenes which product will be favored as the major product. In our next lesson, we'll talk about an additional reaction that conjugated dienes can do that isolated alkenes cannot do by themselves.